Hey guys, today we're going to continue talking about our tangents. So we're going to jump over to page 374 and we're going to talk about a new theorem. So this theorem states if two segments from the same exterior point are tangent to a circle, then they are congruent. So let's say we have circle, we'll use their example, circle D, and we have point B way out here. And we have two segments that are tangent and they meet at the same point. So they go to point B and we'll be tangent right here, say at point C. And then over here we're going to be tangent and, oops, that's way off. We're going to be tangent and we'll intersect at B. There we go. And this will be point A we have. So if AB is tangent to circle D and BC is tangent to circle D, if both those segments are tangent, then they're going to be congruent to each other. AB is congruent to CB. So they come from the same exterior point and they're both tangent. You could do a quick little informal proof of this if you want to. So the concept here is, well, if you go to the points of tangency and draw a nice little segment to them, actually draw the radius to them. The radius is going to be congruent to itself. From a past theorem, we should know that it's going to create a right angle with both of them. And then if you were to sketch or draw in the segment DB, that's congruent to itself, obviously. And if you look, you have two right triangles that you make there. And through your hypotenuse leg theorem, you'd be able to conclude that they're congruent. And thus, through CP/CTC, your two segments are congruent. So in a circle, if you have an exterior point, like we just saw with B, and from that point you draw lines of tangency, right here, a couple tangents, then those two are going to be congruent to each other. So this would be congruent to this. And this can be really useful with finding measurements, especially when it comes to finding missing measurements in what we call circumscribed polygons. So we'll do some examples with this, but first we're going to define what it means to be circumscribed. So being circumscribed means that every single side of a polygon is tangent to the circle. It has to be all the sides. So let's say we have a circle here, and let's say we want to make a triangle that's circumscribed. Well, the triangle is going to be tangent there, going to be tangent here, and tangent here. So every side of the triangle needs to have a point of tangency with the circle. You could have a quadrilateral that's circumscribed. It would just mean every single side of the quadrilateral has to be tangent. So here I'm going to have to adjust a little bit. We have to make sure that we're tangent over here. So every single side would need to be tangent. If you were, let's draw a better circle than that. If you were a triangle that maybe looked like, or maybe look like this, you're not circumscribed because not every side is tangent to the circle. So here, these are two examples of being circumscribed. And from the past, we would say here the triangle is circumscribed about the circle. We would say the circle is inscribed in the triangle. So the triangle is circumscribed about, and the circle is inscribed in the triangle. So if we have that, we can apply this theorem now. Let's take an example. We have one on here. We have an example with a circle G actually, and we are given a triangle that is circumscribed about circle G. Looks like this. It's triangle ABC, and we have point E here. We have point D here and point F on the bottom. Those are the points of tangency here. So AD we're given is 8, EB we're given is 7, and CB, the whole length, we're given is 10. And we're in the units of feet here. So from this new theorem that we just saw, if we want to find all the missing measurements of this triangle, like let's say we want to find the, actually I think we do want to find the perimeter of this triangle, then we can use the theorem we just saw. An exterior point has two segments that are tangent. Those segments must be congruent. So AD should be congruent to AE. So that should be 8. EB should be congruent to FB because it comes from the same exterior point, and we have two segments that are tangent, so this should be 7. If our whole length is 10 and that's 7, then this should be 3 over here. And then because from point C, that's your exterior point, creates two tangent segments, we should know this is 3 as well. So then to find your perimeter, well, you simply just have to add up. There's 10, there's 20, there's 36. So your perimeter would be 36 feet for this. So just like that, we have the perimeter of the polygon. So using this theorem, it can help you find missing side lengths. And just like that, we're all done here. Alright guys, I'll give you some IXLs to try. Have a nice day.